Thank you so very much, for your very nice introduction, and also thank you very much for the invitation. It's really a great pleasure for me to give a talk here. Unfortunately, as said, I cannot be there, but I hope also this virtual talk, is interesting for you. So let me start by sharing my screen. Okay, so I think we all know how tremendously successful AI is these days, but we also know at the same time that there are still major problems with reliability. And in this talk, I would like to take you on a tour through what the key questions are concerning reliable AI, where we stand right now, and what are still challenges, and also what are limitations which we then need to overcome by maybe a bit more unconventional methods. So if you look around us, we see that AI is already, let's say, in various places, in public life, in the sciences, in industry. Some people say we are right now at the beginning of the fourth industrial revolution. So, think of, for instance, self-driving cars, robotics, telecommunication, then also more sensitive areas like, for instance, the whole legal system, maybe not that much in Europe at this point, but in the US, this is already more or less standard, but it will come in Europe certainly as well, and also the whole job sector. And then, the whole area of sciences, from medicine, robotics to astronomy, up to the humanities, like the humanities. And everything got, a new, let's say, push again, as we know, by the appearance of ChatGPT. And I think, as said, we are at the beginning of the fourth industrial revolution, which will, I think it's not only my opinion, but of many people, which will radically change our society in basically every aspect. Now, in the area where I come from mathematics, also there, we see a tremendous impact. It already started in 2012 in the area of imaging sciences, inverse problems. So most of these are of an inverse type. You have to invert, let's say, the measurement process, like denoising, edge detection in painting, and so on and so on. And what was interesting, this is actually the area I come from originally. What was interesting is that basically after 1 year, if you went to conferences, almost 80% of the talks used those type of new approaches, and these led easily to state-of-the-art algorithms. Why these learning types, let's say, approaches are so useful in this area? Well, because there's no rigorous model for what an image is, so that makes learning type approaches so effective. There's another area in mathematics which is also now significantly changed, which is the area of numerical analysis of partial differential equations, so modeling of natural phenomena. There, it was a bit slower because, a PDE is basically a rigorous model. So the question is, what is there to learn? But what turned out is that in the high-dimensional regime, these methods, like, for instance, neural networks, are easily able to overcome and beat the curse of dimensionality. And so from that point on, from 2017 on, also that area was significantly changed. And so this, these type of changes we see basically in every area of science, as said, every area of human life, of public life and industry. On the other hand, there are also voices which are a bit more cautious. So this, this is an interesting incident now. Already 5 years ago, where, one researcher won an award at one of the big AI conferences. Ali Rahimi gave a plenary speech, and in his speech, he claimed that machine learning, and in that sense, artificial intelligence, is still at a level of alchemy. And his argument was it's a lot of trial and error. People don't know which architecture to choose over another, why some algorithms work and others don't. Now, the last 5 years, we have done a lot of research, in particular in the foundational areas, and we are much further. However, if you train a neural network, you might realize that it's also still a lot of trial and error, testing how many layers to take, how many neurons in each layer, and so on and so on. So in that sense, we still have a long way to go. And then there are also people who are even more cautious, like, for instance, Stephen Hawking, who said the development of full artificial intelligence could spell the end of the human race. Yeah, so that sounds very scary. From my viewpoint, there's not that much danger, because the way we develop artificial intelligence is by, in a certain sense, also developing algorithms which are controllable. But certainly, the danger in this respect is always the humans who use AI. And so this is something which is very difficult to control. And as I said, I mean, there are, let's say, these warning voices, and indeed there are also several problems. So for instance, there are problems with safety. I mean, we all know there were already various accidents involving robots, and after all, a self-driving car is nothing else than a robot. There are problems with security. One can hack into these cars, one can hack into hospital systems, modifying things slightly so that it's not, let's say, observed by a human, but still the AI will make a radically wrong decision, which is a huge problem. Problems with privacy, I mean, in particular in the healthcare sector, data is very scarce. And so what happens is that worldwide, there are basically privacy violations on a daily basis, in particular in the healthcare sector. And then last but not least, I might say problems with responsibility. If you look at these algorithms, many of those are black box algorithms. We don't know how decisions are reached. And also decisions can be very biased, depending on usually also a biased set of training data. So in that sense, I think it's fair to say that one major current worldwide problem is the lack of reliability of AI technology. And certainly this was observed also in politics, and so me coming from Germany, so in Germany, we, for instance, have an AI strategy of the German federal government. The EU now has the AI Act of the European Union, and the G7, I mean, when they met in Japan in the summer, they started the Hiroshima AI process. There are new documents also now, which gives, let's say, recommendations if you set up AI technology and you would like to do that in a human-centered and also reliable manner. So there are a lot of activities in that direction. That if we look closely what it takes to get reliability, we observe that what you need is a profound mathematical understanding, because without a deep understanding, there's no way you can get true reliability in the end. There will be always a lot of uncertainty. And so I said I would like to take you on a, let's say, tour now through reliable AI from a, let's say, theoretical, foundational mathematical viewpoint. Okay, so let's start. And I would not like to cover everything in AI, but focus on deep neural networks, which are, in a certain sense, the workhorse today of artificial intelligence. So this will be, let's say, the running architecture which we will use in this talk. Deep neural networks are nothing new. They were already introduced by McCulloch and Pitts in 1943. What they aimed to do is they wanted to indeed introduce artificial intelligence. And the way they did that was, well, I mean, at least we humans believe that we are intelligent. So what they aimed for was to mimic the human brain. The human brain now, as we know, consists of neurons, which are interconnected. And so what they did was they modeled each neuron. So they did in artificial neurons, which they then connect. And so here, this is an artificial neuron. It's a function. So in these x1 to xn are signals which enter the neuron. And then what happens there is a weighted sum is computed. It is compared to a threshold. And then the activation function determines to which extent the neuron fires or not. And these are connected in layers. So this is standard feed-forward neural network. We have here the entrance layer, the output layer. And so here, each one of those is such an artificial neuron. And if you connect those, you see that such a neural network is nothing else than a mathematical function, which is highly structured in this way. You see the composition of these TL, which are affine linear functions. You see the weights and the bias terms. And then we have these nonlinear activation functions, which are univariate and applied component-wise. And so in neural network, what is then later on trained, and the free parameters are these weight matrices and the bias terms. So depending on the training data, these can be modified. Okay, so what are now the key, let's say, theoretical questions in this regard? For that, I would like to take you once through a workflow of how to apply deep neural networks, and then we will see which, let's say, main questions arise from that. Okay, so what is the key problem? I mean, you want to learn a highly complex function or distribution, but you just have sample values at hand. So typically, let's say you have images which lie on a low-dimensional manifold. Natural images are always assumed to lie on some lower-dimensional structure. And let's say you want to classify cats from dogs. So the cats are mapped to the value 1, the dogs to the value 2. But you just have a couple of images and you have their labels. So now what to do is you split it into the test in a training data set. The test data set you set aside and just consider the training data. And now the goal is to approximate F by a neural network. So you first have to decide which neural network to take, or which class of neural networks, so how many layers, how many neurons in each layer. And so this is, this is what we already said before, this trial and error. It's a lot of testing, which, let's say, architecture behaves maybe in a beneficial manner. Once that is decided, the neural network is trained. So that means the weights and the biases are trained on the training data set, so that the neural network, if you put in training data from here, you always get the correct answer. So you tune the free parameters that way, and the way to do it is by what's called stochastic gradient descent typically. And so then you have the neural network in the end, the fixed function, and then you apply it to test data, and you hope you also get the correct answer. And so this is testing to which extent the neural network is able to treat out of sample data. Okay, so this leads us to the key theoretical questions. One is, sorry. Sorry, one is what is called expressivity. So this asks the question which network architecture to choose. So how many layers to take, how many neurons in each layer. How many neurons in each layer, which activation function. So this is typically a pure approximation theoretic question. And so also, for instance, applied harmonic analysis comes into play there. Now, the second point is learning. So which type of learning algorithms do you use? What is typically used these days is stochastic gradient descent. And for some reason, although the problem is highly non-convex, it typically gives good local minima. And so, to answer that question, usually optimization, optimal control is used. Also, let's say a bit more exotic areas like algebraic differential geometry to understand the shape of these local minima. The next question complex is generalization. So we train our neural network and then we are wondering how it behaves on test data. And what we aim for are error bounds. And so in this area, what is typically used there is learning, statistical learning theory, statistics, and so on. And this is also absolutely crucial because, many areas today do not use deep neural networks at present because these error bounds are to a large extent missing. Think, for instance, of electron tomography. There you don't have a ground truth. Basically, you only have access to the ground truth through your algorithm. So you need to trust it completely. And unless you don't have, let's say, precise error bounds, they will always stick with Fourier type methods and not, let's say, go to learning type methods or AI. Okay. So generalization is a key question. It's sometimes also called the holy grail of the theory of deep neural networks. There's another area which I find also very important, which is explainability. So this discusses the question, I have a fixed neural network, and I'm wondering how decisions are reached. I have a certain decision, and I'm wondering which, let's say, parts of the input data, which features of the input data are responsible for that. And this is also for legal reasons very important, because I talked before about the, for instance, EU AI Act, and the right to explain is also explicitly in there. So a customer always has to have the possibility to ask, why was a certain decision reached? And so this is, for instance, uses methods like information theory, uncertainty quantification, and so on. So now I would like to delve a little bit deeper into the area of generalization and explainability. Generalization because, as said, these success guarantees are in a way what we aim for in the end. And explainability because, also for legal reasons, this is something which every AI technology in the end has to satisfy and has to provide. Okay, so let's start with generalization. I would like to give you each time a bit the flavor and also show you one result as an example of that area also where research stands today. So what is, noteworthy in this whole area is that neural networks perform extremely well in the high dimensional region. Then, let's say the generalization error is very small. So therefore, practitioners always say, well, take the largest neural network which still fits in your GPU. And so there's this very famous double descent curve which shows this phenomenon. So let's take a look at that. You look at the left-hand side. So this language is a statistical language. Here we have the capacity of the hypothesis class. So this is the size of the neural network, and this is the error. Now, as the neural network, the size grows, the training error will go down because the network is certainly better able to fit the training data. But the test error, after some point, goes up. And this is this phenomenon of overfitting. So the network aims to enclose the test data too good so that new samples are easily misclassified. Now, and this is very well explained by statistical learning theory. But what happens these days is what we see here on the right-hand side. Yeah, you see the left-hand side coincides with what we see here, but then after some point, the test error goes down again. And this is this modern regime. Yeah, and so you see here it goes often, it becomes much smaller than it became here. And so therefore, let's say the slogan in that respect is the larger the better. And there are a lot of approaches aiming to analyze and understand that, like we see dimension, radar matter complexity, neural attention kernels, and so on, all to explain this phenomenon. I would like to now show you one result, which also takes us to, I think, a very exciting area, which is today, let's say, receives a lot of attention, which are graph neural networks. So graph neural networks can be viewed as a generalization of classical neural networks because Euclidean data, after all, you can also view as a graph. So a linear graph or let's say a pattern, a graph on a grid. So a graph is nothing else than a map from graph nodes to RC. So basically we have a graph, and for each node we now assign a feature vector. And so the graph neural networks are able to handle this type of data and process it in a certain way. And this has numerous applications. So for instance, recommender systems, companies require graph neural networks, and the whole social media, say, regime, like also fake news detection requires it. Also, for instance, chemistry, a molecule is nothing else than a graph. So also their graph neural networks are used. Now, we want to ask these generalization questions. And again, certainly what it boils down is you have a graph neural network. It has graphs of signals which are in my training set. And now I want to ask, does it generalize to unseen data? So let's say my graph here on the right-hand side is my training set. And I'm asking, I trained my neural network, can it then also deal with this graph on the left-hand side? And there's a sub-question you can ask here, which doesn't appear in Euclidean data. Because now you can ask, I have two graphs which model the same phenomena, whatever that means for now. Yeah, so you see here, these kind of look alike. So let's say you have one of these graphs in your training set, and then you have a graph which model the same phenomena. And then for those, you can ask, does then the graph neural network has the same repercussion also on that? Yeah, so this is a sub-question of, let's say, the full generalization question. And this modeling the same phenomena can be defined in various ways. It could be that you have some continuous space and both of these graphs are sampling of that. There's also something which is now called a graphone. It's like a continuous limit object of graphs. And if you have two graphs which are in that sequence converging to that, then you can say these model the same phenomena. So there are various ways to take that. And in that case, we can actually give precise error bounds. And again, I just want to give you the flavor of it, not going too much into details. So one can use filters, spectral filters, weights in the spectral domain, comparing, let's say, the action always via this continuous space, which overlay both graphs. And then we can show very precise error bounds. And again, I don't want to give, let's say, the details here. Let me just say that this transferability error, so the error from using one or putting one of these graphs in the neural network versus the other, you can precisely estimate. And so in that case, I mean, this sub-question we can answer completely, and there are various other results now also, for instance, for message passing graph neural networks, where you can show similar results. So this is, as said, I mean, maybe a bit the holy grail, what we want in the end. We want to have very precise error bounds on or success guarantees for unseen data once we train the neural network, or here in that case, the graph neural network. So there's a lot of research going on in that direction. Now, explainability, as said, deals with a bit different question. There we already have the neural network. We don't even know how it was trained. And then you want to analyze how it reaches decisions. So what these algorithms typically do in a nutshell is the following. Let's say I have this 3. And let's say I have a neural network which correctly classified this as a 3. And so then these explainability approaches put heat maps on this image, which indicate at each point how important or relevant that pixel was for the decision. And so here, this network, which correctly classified this as a 3, looked a lot at these openings and at this curve. And this also makes a lot of sense because these openings distinguish a 3 from an 8. But I mean, from a, let's say, theoretical viewpoint, one can then ask, I mean, these heat maps look nice, but what does it precisely mean? What is relevance exactly from a, let's say, foundational approach or from foundational viewpoint? What about optimality? We always want to have optimal algorithms. What about other modalities? I mean, a lot of these algorithms just focus on imaging sciences and images. And what about higher level explanations? Because typically, or often, not every pixel is relevant or not, but maybe a combination of pixels. And so the ultimate goal would be to question the AI as a human about the reason for a decision. And we're a bit further now also with ChatGPT, because there, I mean, it helps with, let's say, the natural language processing side, but still, I mean, we are far away from this vision. And something which one should also keep in mind, because if we want to use explainability to ensure reliability, the explainability approach itself needs to be reliable. Yeah, I mean, you cannot just produce fancy pictures like that. And from my viewpoint, therefore, it is important that the explainability approach itself has some theoretical underpinning to make that reliable, and then can use it to ensure that the AI is reliable, or here the deep neural network. Okay, so let me also show you one approach in that direction, which uses information theory. Now, information theory comes from electrical engineering, communication theory, and it's so it asks the following question. I have, so maybe just take a look here. I have 2 persons. One has a message. She transmits part of the message to Bob, and Bob decodes it, and then hopefully recovers the complete message. Now, this is typically called rate distortion theory. So Alice transmits some bits to Bob, and that's the rate. You would like to keep the rate small. Bob decodes it and will make an error. So this message, which then Bob has, will be to a certain extent different from the ones Alice sent. And that's the distortion, which you also want to keep small. Okay, so now we can phrase this whole explainability approach in this framework. Let's say Alice and Bob both have the neural network, and Alice also has the original image. Now, she's allowed now to transmit parts of the image to Bob, hopefully the relevant parts. Then Bob needs to first bring it back to the image size by, let's say, obfuscation with random pixels. He puts it in the neural network and will get an answer. So the goal is now to transmit as few pixels as possible, to have concise explanations, but also to keep the distortion under control. So the distortion is the difference squared and the expected value. Okay, and so this question, keeping, let's say, the number of pixels small and the distortion small, that's what's called the rate distortion function. So you want to keep the distortion under control while minimizing over the number of pixels. And if you work in approximation theory, you know that this is hard to solve. In fact, I mean, one can show that it's NPPP complete. So finding a minimizer is extremely hard. And if something is very hard, well, I mean, you relax. And so, in fact, I mean, what one can then solve is this relaxed version. You see now, instead of just having a pixel being relevant or not, we assign each pixel a relevant score between 0 and 1. And then we minimize the distortion, and at the same time, we minimize the L1 norm of these relevance scores, and this promotes sparsity of those. And so this one then also allows us to have a rigorous mathematical performance analysis, because we based it on the information theory and a theoretical framework. So here are a couple of images. Let's say this is an image which was correctly classified as a dog, and here are some then explanations which different approaches gave. And so you see here ours, which is very much tuned towards conciseness and sparse explanations. Now, very few relevant pixels. Yeah, and this looks nice, but certainly you always would like to maybe compare on a bit higher level, and you can do it this way, for instance, where we have this graph where here you have the number of relevant pixels, the rate, and here you have the error. And you see ours goes down the fastest. Now you can say, okay, this is very unfair because your approach is tuned towards rate distortion. And to a certain extent, I agree. However, if you look at these other approaches, how they evaluate their, let's say, goodness or success in a sense. And so what they do is they also look at the pixels and their relevance scores, and they sort them. And then they start flipping at some point with random pixels and look when the decision flips. And that's basically exactly what this figure does. So in a certain sense, also the other algorithms look for this measure. Okay. Now, I mean, you can ask, first of all, I mean, obfuscating with random pixels looks very strange. I mean, we can certainly believe that random pixels the least distort the meaning, but the generated image looks extremely awkward. And so you can replace this, for instance, by a painting gun to produce more natural images. But for that, you need to know the data manifold. Now, so if you don't have any information about that, you have to go with the random pixels. A bit more interesting, maybe, is to go from pixel-based explanations to higher-level explanations. Now, in imaging sciences, there are different representation systems where you can represent your image as. Wavelets is one example. It's actually the basis for the JPEG 2000 compression standard. Now, so here are a couple of wavelets. And so you can write your image as a linear combination of wavelets. And so what you can now do is you can assign the relevance scores not to the pixels, but to the coefficients of your decomposition. And so this led to the approach Kutyniok, which we called Kutyniok. And interestingly enough, this has a lot of similarities with compression. So let me show you that. So just to recall what image compression does. I have my original image. I compute a representation, say wavelet representation. I take the largest entries and I replace the others to 0. That gives me the compression. And so I only save those which are not equal to 0. And then if I want to reconstruct, well, I reconstruct from this, and I hope that I get an image which is close to my original image. Yeah, so that's image compression in a nutshell. Now what we do here is we again have our original image. Let's say we compute the wave decomposition. We select largest entries. And now we replace the others with random noise. Now, or we use this in painting gun, for instance. And then I reconstruct. But now certainly I cannot expect, and also this is not what I want, that this image is close to my original image. But what I want is that through the lens of a neural network, they are close. Now, so this is this distortion which I need to compute. So in that sense, it's very much in the spirit of compression. And so what you can do is this is, for instance, what you see here. So this was a task from telecommunication. You have a city map here, these blue buildings. You have these red dots, which are cell phone users, and you have the data, how good their reception is. And this white area here is a cell tower. And the neural network computed this black and white background. And what it indicates is that each point, how strong the signal is at each point. So for instance, here it's very bad because you have a lot of buildings between you and the cell tower. Okay, and now you can wonder why you have this black area here. Yeah, because if you stand here, you stand right in front of the cell tower. Yeah, and this is the explanation. And in fact, these cell phone users have bad reception. And so it seemed to make sense to put this black area, this area of bad reception there. And so what turned out later on was there was actually a building missing in the city map. So that way you can understand it says here seemingly wrong decisions. Now, here the network did something really wrong. It classified this as a diaper, although it's obviously a man with a dog, and it classified this as a screw, although it's obviously, a man with a sweater carrying something. And so now I can overlay this with this wavelet-based explanation, and we will see what the network has seen to reach that wrong conclusion. So I will put it on top. And then you see this looks a bit like a baby. So then a diaper is not that far off, and this looks a bit like a screw. And so, then you can basically correct for that and retrain to a certain extent to get rid of these wrong decisions. Okay, so these were, let's say, two glimpses into explainability and generalization, which I think are extremely important. Generalization is the reason because these are the overall success guarantees which we require, and explainability, because for legal reasons, this will be a requirement in the future for any AI approach. So let me now also say something about if we apply deep neural networks to large problem classes. One is certainly classification, but here I would like to, let's say, look at a bit more interesting ones, which I already mentioned in the beginning. One, as said, are inverse problems from imaging sciences, so asking how do we optimally combine typically deep learning, deep neural networks with model-based approaches. And one can also say very provocatively, maybe we are able to replace specialized numerical algorithms in the future at all. And the area of partial differential equations, where more, let's say, the punchline is, why do these approaches perform that well in the high-dimensional regime? And here I would like to delve a little bit more into the first part. Okay, and while doing that, we want to, let's say, discuss in particular how to ensure reliability while doing that. So imaging sciences is a large area, but basically, most problems boil down to solving what's called an inverse problem. So let me first discuss just on 2 slides what has been done, and then we will see why there's a need to go beyond that. So the question is the following. I have an image F, let's say this image here, which you see here, the K, the operator does something to it, maybe takes some parts out. I have this G, and now from the G and the K, I would like to recover F. Yeah, so I would like to invert this K. So K could be also a measurement process, like, for instance, computed tomography, something of that type. And this I would like to invert. From the measurements, I want to go back to the original image. And one classical approach to solve this problem is by what's called sparse regularization. You see here, we solve this optimization problem. If we bring this down to 0 while minimizing over F, we have solved this problem exactly. And then certainly, I mean, there might be numerous possible solutions F for doing so. For instance, in this case, we can fill these black gaps with whatever we want. But to ensure that we get a natural looking image, we have this regularization term. And so here, sparse regularization has the philosophy that there will be always a representation system which gives you a sparse representation. And so this L1 norm, as already said, promotes sparsity. Now, for these phi i's, we can use wavelets. That's one possibility. There is another possibility which takes more care of the fact that in imaging, typically we have directional structures. So what we proposed at some point, or no, some time ago, was to use shearlets, which are more directional based. So they appear on any position, on any scale, and on any direction. There are nice theorems which also show that they give you the optimal compression rate for certain model classes of functions, and there are a lot of algorithms available. Okay, so sparse regularization with shearlets is one very classical method, but as said, this has certain problems, and we need then, I mean, AI-based approaches to overcome them. So let's look at one of those problems, and this takes us in the world of medical imaging. So computed tomography is, I mean, a very standard approach. What it boils down on a, let's say, mathematical side is it computes the radon transform. So I have the human body here, I compute line integrals. This gives me one slice of the sinogram. Now the sinogram, and then I rotate the machine. And that way I fill the sinogram, and from that I would like to recover the interior of the human body. Yeah, so that can be done with very high accuracy. The problem occurs if we not have enough data. So for instance, we don't want to expose the patient to too much radiation. Basically, maybe we only want to compute every second angle. So that's called low-dose CT. Even more serious is what's called limited angle CT. So for instance, electron tomography, we cannot turn this device by 180 degrees. So that boils down to the fact that from the sinogram, we have a whole chunk actually missing. And that's very difficult to compensate. And so this causes these problems, which you, for instance, if you have a 60-degree missing angle, which you see here, if you have a 60-degree missing angle, standard reconstructions are extremely bad. And so this sparse regularization with shearlets, which we discussed, is better, but not exacter. Yeah, so you see, I mean, there's a lot of blurring here and everywhere going on. And the reason this is so difficult now is that this type of data is just too complex to precisely model mathematically. Yeah, so this regularization term is only an approximation, but I mean, it's not good enough to give very good reconstructions if you have this whole chunk of missing data. So that calls now for learning type approaches. And there is a whole world, I mean, at this point, out of these hybrid approaches. Now, I mean, certainly you can always train a neural network end to end. Forget everything about physics you know. But this, I mean, as one can understand, if we have additional knowledge, like physical knowledge, the physics of the measurement process, why throw it away? Why let the neural network do the heavy lifting and expose it to even more, let's say, uncertainty? So therefore, these hybrid approaches are extremely popular, combining traditional methods with model-based, traditional methods with learning and AI type approaches. So for instance, one can incorporate the information of its operator in the neural network. There are these what's called plug and play approaches. So we have the traditional algorithm for recovery. We substitute certain parts of it by neural networks like plug and play and so on and so on. Then there are what I might call semi-supervised approaches, we encode the regularization by a neural network. So it means these neural networks we don't train on the full data set, but in a very special way, so therefore semi-supervised. So these are like these adversarial regularizers, for instance, by Carola Schönlieb and collaborators. And then there are what's called maybe unsupervised approaches. So we just parameterize the solution as the output of a neural network. So these deep image prior, we assume that what comes out of a neural network is like a natural looking image. And what I put here is, I mean, in all of those approaches, the neural network has typically a U shape. So these are the so-called U-nets. For some reason, these are best for imaging sciences. You see a U-net. We start here at the image size, we bring it down, so we compress it in a certain sense, and then we bring it back up to image sizes again. And there are skip connections to transmit some information which might otherwise has been lost. So now here, I would like to show you one particular hybrid approach, which follows a philosophy I like a lot, which is to use model-based methods as far as possible and as far as they are reliable. Because there we have these error bounds, and to my mind, it doesn't make sense to replace everything by neural networks and by AI. Then use AI-based methods only when they are necessary and then combine both. Now, so this has, as said, the advantage that we have theoretical guarantees from the model-based method. We have reliability in that sense, since we only use neural networks where otherwise the classical methods fail. We have a better performance because neural networks do something much more specialized, and it's less than a black box, as a black box. Okay, so in this case, I mean, if you go to limited angle computed tomography, so for instance, we first solved the problem with sparse regularization using shearlets that gave us these not that great images. Then we used another shaded transform, which exposed which parts had already been very well recovered and which not. And only for those, we then trained a neural network to recover those in the shielded domain, and then bringing back everything to the image domain to combine those. And so here are those images. So these we already saw. This is, let's say, an end-to-end approach, already better than, let's say, the classical approaches. And so if you combine both in a careful way, you get much better approaches. And so there are now, I mean, also in this direction, even more sophisticated approaches using microlocal analysis and a lot of fancy tools to improve on this, let's say, basic strategy even further. Now, okay, so this was now an excursion into, let's say, one very classical area where people apply neural networks, and it is discussed in a certain sense how you can do that in a, let's say, reliable manner, because as said right now, neural networks are not as reliable as we want them at this point. So therefore, it seems a good idea to combine that in an optimal manner with model-based approaches. Now, so this slide we already saw, and what I would like to mention now in the last minutes is one direction which I think is often overlooked, but which requires, to my mind, much more attention. And this is the question whether there are fundamental limitations. I mean, it's a method. Neural networks are a certain method, and they will have limitations. Right now, I mean, also industry believes that you can throw a neural network on every problem. Yeah, and I think this is a bit risky. I think one need to really carefully think about where to apply it, but also where to not apply it and where fundamental limitations exist. And so here, I would like to show you just a little bit concerning computability. So as said, I mean, neural networks and artificial intelligence in general is not a Swiss Army knife. It has limitations, and one viewpoint one can take is what can one actually compute on digital hardware, because problems are usually of a continuous type, in particular in imaging sciences. So we have something at different resolutions up to, let's say, infinitely small resolution. And if we compute things on digital hardware, we break everything down to zeros and ones. So this needs to have certain limitations. And so the computable problem, in a nutshell, is one for which this input-output relation can be computed for any given accuracy. If something is not computable, well, I mean, you can certainly still solve it on your laptop and on your computer. But then, I mean, you need to be happy with limited precision. And also, I mean, since things are not computable, you don't have a guarantee for correctness. So in particular, if you aim for reliability, this is a serious problem. And there's a very nice model for digital computers, which is very well accepted, which is a Turing machine. Now, so a Turing machine, I don't want to discuss it in too much detail. It's a strip with some, let's say, with some head doing some computations, but let me just stress this is what is now, let's say, considered the idealization of a digital computer. In that sense, what you can compute on a digital computer, like a GPU or a CPU, you can compute on a Turing machine and vice versa. And as I said, I mean, scientific computing, most problems are of a continuous nature. And so what we could show is that, in fact, I mean, the solution of a finite dimensional inverse problem is not Turing computable. Yeah, and so let me say, I mean, there was also previous work, for instance, by Anders Hansen, where they considered an Oracle Turing machine. So this is slightly a bit stronger result, showing that, in fact, for finite dimensional inverse problems, like in this whole area of imaging sciences, things can be not Turing computable. So this is certainly unfortunate, because today, and I'm sure you also have laptops in front of you, computations we perform almost exclusively on digital hardware. So that means we cannot find an algorithm for which we get an arbitrary good accuracy. The output is not reliable in that sense, and it could be why we see these instabilities and non-robustness for deep neural networks today. And it could also be why if you look, for instance, at this whole area of self-driving cars, we are not as far as we hoped. Also Elon Musk, thought we would be much further at this point. Throwing a lot of money on it, but there seemed to be some fundamental barrier why we cannot overcome these instabilities and non-robustness. So the question is, what to do? Because that seems very unfortunate. And as said, this usually then calls for a bit unconventional solution. And so what theory then tells us is that, in fact, things become computable if you go in the analog world. There's something which is called a Bloom-Schupf-Smedley machine, which deals with, to a certain extent, real values. And so there things become computable. That means reliability in certain problem setting might call for novel hardware, and there are very exciting directions. Yeah, so for instance, neuromorphic computing, there are the neuromorphic chips, which are already being produced these days. There's biocomputing, there's quantum computing. And so let me also mention maybe a different issue right now besides these reliability problems. I think we all know that GPUs and GPUs in particular are extremely energy hungry, which is a huge sustainability problem. And also their neuromorphic chips are significantly better. Quantum computing will not solve the energy, most likely not the energy problem, but the neuromorphic computing. These are much more energy efficient chips. So these might solve both the sustainability problem and also the reliability problem. And so the question is, maybe not get rid of the GPUs completely, but maybe augment them by these novel type of hardware in a certain manner. And let me say, there are many more problems which we showed. For instance, some classification problems are not computable, the pseudo-inverse. Also, if you go to very easy partial differential equations, they cause what's called a complexity blow up. So in that sense, that if your input is has a certain complexity, that then the output is an exponential higher complexity, and also for some optimization problems, this can be shown. So the vision for the future from my direction would be, if you want to go to really truly reliable AI, you most likely need to go to next generation computing. So let me finish with some conclusions. From my viewpoint, we live in really exciting times. AI shows impressive performance for real-world applications, but there is this caveat that we still have a major problem with reliability, and there are several instances where we realize this obstacle. Now, we then discussed a bit, what you can do from a theoretical perspective, because from my viewpoint, to get to reliability, you need to go deep and need to understand things from its depths. So expressivity is one direction, learning, generalization, explainability. We delved a little bit more into generalization and explainability because, as said, these generalization bounds are key to ensure, let's say, safety. And explainability is something which also for legal reasons will be required basically for any AI technology in the future. We also discussed a bit the application setting here in the terms of imaging sciences. Ingress prompts were typically one, I think from my viewpoint, very interesting direction and goal should be to optimally combine AI with model-based approaches. And then in the end, we also discussed what I think is unfortunately often neglected, namely limitations of artificial intelligence, and discussed that there's a problem with digital hardware which might lead us to and force us to, or encourage us to, even to go to next generation computing. And so before I stop, since we talked about reliable AI now for a long time, let me also mention that actually in Munich, we just set up a Konrad Zuse school with the specific topic of reliable AI between both universities there, the TU Munich and the LMU. And as you see here, the areas which are taught there for master students and also for PhD students is in particular mathematical and algorithmic foundations. And then there are other areas like medicine, healthcare, robotics, interacting systems, algorithmic decision-making. So the idea is to ensure not only technical brilliance, but also this awareness of the importance of AI's reliability in all of those aspects: safety, security, privacy, responsibility. And at this point, I would like to stop and thank you very much for your attention.
Okay, thanks a lot, Gitta, for the very interesting talk. Now I think we directly go to questions.
Yes, thank you very much for the interesting talk. I guess, one thing I was curious about is the non-computability aspect. So is it, in your opinion, a mathematical curiosity, or are there physical systems that you can predict are non-computable?
So this is, Turing machines, first of all, you have to believe that Turing machines are the correct, let's say, mathematical model for digital computers, which is, I think everybody believes that. Yeah, and then, if you show something for Turing machines, you can directly transfer it to the physical world. So it doesn't mean that for every inverse problem, there's let's say, an obstacle, but it means that there exist inverse problems for which these problems occur. And so for those, you might need to design the algorithms specifically for a given accuracy. So in that sense, yes, it's the problem is indeed there in the physical world.
And just maybe a curiosity now. So you mentioned quantum computing, right? So do you have any argument where, I don't know, a quantum Turing machine can be more powerful from the computability point of view?
Oh, so I should say, okay, so quantum computing, what I mean is those quantum computers which are not qubit quantum computers, because if you use qubits, then again, you break it down to, let's say, the digital world. So those will not work. It needs to be, let's say, the true quantum computer. So for instance, in Munich, we have Emanuel Bloch, who does optics.
Photonic, Okay, thank you.
Hi, thanks for the great talk. I wanted to ask about explainability. And one thing, so I've done a bit of work in this area. One thing that seems quite clear to me is that a lot of neural networks are kind of computing higher level conceptual features internally to make their predictions. And I wondered, from a theoretical perspective, do you have any thoughts on how you might extract this? Because the aspect of going into the wavelet space, for instance, there's not really kind of a wavelet for dog nose facing left. Can you say how this sort of problem appears to you from the theoretical side?
Yeah, so that's a very interesting question. What are, let's say, the correct features? There are a lot of approaches now. There are these super pixels where you have, let's say, fixed combinations. What people sometimes also do, they do a segmentation of the image and then put a relevant score for each of these segments. So I don't think there's a, let's say, an overall general answer to that. It depends very much on your application. In that sense, I think explainability is a very exciting, but also very interdisciplinary area. And it depends very much on what you would like to have and what an explanation is. Because also if you talk with a human, humans give deep explanations in different ways, even on their, let's say, depending on their cultural background. So in that sense, I don't think there's a general answer. From a mathematical viewpoint, I mean, you need to find a way to specify these features. Yeah, so we used wavelets. I mean, we also use shieldlets. There could be superpixels. And then you can design your approach. But I mean, which features are the best is also very difficult to optimize over, because it's not really clear what your optimum in that sense is. You can optimize certainly for, you want to have as few relevant objects, features as you want, but it's not clear whether this gives you the best explanation.
Yeah, I'm thinking of phenomena where like a neuron or a direction in activation space will activate in the presence of some particular kind of macro scale feature of the input image, for example, or a phrase in a large language model. Mm-hmm. So maybe you're familiar with Chris Oler's work in this space, for instance. Like, I'm thinking of, there's some quite clear empirical results, but I'm clear, like, there's basically nothing theoretical done.
Yeah, I mean, this is also, I think, in general, very, very difficult to do theoretical work in this setting, because it's difficult to have a ground truth. Typically, you don't have a ground truth. I mean, already natural language processing, it's very difficult to, let's say, do, in that sense, theory. So I don't know. I mean, I wouldn't just think about it, but at this point, I would be a bit, let's say, cautious to say you can get, let's say, profound theoretical underpinning. I mean, here what I meant is, I mean, this algorithm which we designed, this way distortion explanation, so there you can show, for instance, that it doesn't produce any artificial edges, and so on and so on. So you can do, let's say, there are a bit theoretical underpinning. But in general, it's always challenging.
Cool, thank you.
Hi, thank you very much for the talk. I'm not an expert in this area, but I've been really interested in non-deterministic Turing machines and especially biocomputing for a long time. But whenever I've come across it, it's almost like building a certain, essentially a computer to solve a very specific problem, sort of the digital computer equivalence of, wiring a certain circuit to solve a specific factorization problem. And the computer they're building is not, programmable or anything. So do you know of any certain effort to build a biocomputer like that that's a bit more, programmable essentially, or in that sense, rather than being built for just as a proof of concept for a specific problem?
Yeah, I mean, also a very good question. So I think neuromorphic chips are the furthest developed at this point from what I mentioned. I mean, maybe quantum computing second and biocomputing third. So I'm not an expert in biocomputing, I have to say. So I don't know exactly where the state of the art is, but I mean, right now we only see, let's say, for very specific tasks, and it's not clear whether you can do it in a bit more universal manner. So for neuromorphic chips, this is true. And there are also mathematical models like spiking neural networks and so on. But for biocomputing, it's very hard for me to predict how that will evolve.
Gitta, thanks very much. It's Terry Lyons here. I would like to go back to your slides about generalization, if I could. The earlier ones. No, earlier. Where you had the graphs. You had the two lots of graphs. There, that's the one. Mm-hmm. I would like to challenge you and ask you to explain to me why you think it is reasonable to take a function defined on one set and have some preconceived idea as to how to extend it. It seems to me that this actually shouldn't be doable without a theory of the functions and the class of functions you're trying to use. I mean, it seems to me that there is no real answer to this question. It could be that you want to distinguish big graphs with lots of nodes from graphs with little nodes. And that really you have to introduce a notion of regularity of function of some kind or another before it makes sense. And I'm just a bit worried that people think they should be able to do things like this without doing that. It seems to me we're missing a whole bit of math, actually, before we can do this.
Yeah, I completely agree with you. I mean, there's a lot of math, let's say, hidden. So, I mean, certainly here we look at specific function classes in some sense. So, as I said here, which come from, let's say, digital signal processing, so polyvena spaces and so on. So, in that sense, I mean, I agree with you. There need to be some regularity theory to a certain extent. Otherwise, you cannot do that. And then, I mean, yeah, so as I said here, I mean, let's say the punchline of the proof is always to go by this continuous space, but this you can only do if you live in special function classes. Yeah. So, yeah, as I said, I mean, this was just a sketch of everything, but there's a lot of math hidden. Yeah.
Hello. You suggested that we might need to consider neuromorphic computing architectures, or in more general analog computing architectures, but doesn't that create a problem with error correction, or is that something that people now feel much more confident about, in that you might be sort of switching from something that is hard to compute to something which is hard to error correct?
Yeah, I think for the error correction, I think for quantum computing, there's still a huge problem to overcome. I mean, for neuromorphic computing, I don't think this is that serious at present anymore. So the new neuromorphic chips, I mean, so I'm aware of, I mean, so for instance, around Dresden in Germany, Spinnaker and so on, I mean, they produce a lot of neuromorphic chips. So they're, I mean, I think it's to a certain extent under control. But yeah, I mean, you will introduce maybe some additional uncertainties, and so what we didn't do yet is also a full error analysis, which is still missing. But I believe that this can be overcome. And again, I mean, the second component, the energy consumption, this is something which definitely calls for, let's say, going that step.
Yeah, I think that were all the questions. Thanks a lot, Gitta, for joining us online. And yeah, it's a pity that you can't join us for the coffee break now, but yeah, all the best for your recovery. And yeah, thanks.
Thank you.